We are going to start the summary of this course with an article that Dirac wrote for the Proceedings of Royal Society of London in 1929, so very soon after Schrödinger proposed his equation for quantum mechanics. So the article, the name or the title of the article is Quantum Mechanics of Many Electron Systems. And I'm going to read some sentences I've highlighted here in yellow. And I'll make some comments later. Okay, the general theory of quantum mechanics is now almost complete. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. So, okay, the two comments I want to make is the first one is related to this one, and the second one is related to this point here. Okay, of course, as someone said, as making predictions on it's always difficult, especially when talking about the future, and somehow it's also what happens here. Basically, he was thinking that knowing the underlying physical laws, it's the main aim, and it's enough. And after that, you just have to apply that theory in order to have everything. Okay, it seems so, right? But even though you do know the underlying physical laws, which of course is the starting of everything, it doesn't mean, however, that you can derive everything in a very straightforward way. For example, even though you do know that life is a consequence of the underlying physical laws, and even though you do know which are the physical laws, it's very difficult to conclude from there that life might exist, right? And somehow it also happens the same in material science. In material science, you do have such a number of particles, which is a huge number of particles interacting each other, that even though you do know that which are the physical laws governing that nature, that material science, it's very difficult to say a priori which are the physical properties that the materials may have, right? And some of the physical properties are extraordinarily astonishing, like, of course, like antiferromagnetism, like, of course, superconductivity, superfluidity, and very recently, for example, we have seen these topological insulators, well semimetals, and so on and so forth. Of course, then we are sure that there are still many physical properties that are somehow hidden in the materials, and they have not predicted yet, that are waiting to be predicted. So even though under the knowing which are the underlying physical laws is the basics, the starting point for doing something more. So it's important to have in mind that this is not the only point. So there is a famous physicist whose name is Philip Anderson, who someone said, more is different. And that's what happens in material science. More, we have many particles, it's the origin actually of the huge diversity of the physical properties that you might discover and predict in the materials. Okay, that's the first comment about that. And then I want to make a comment about the second one. He was looking for some kind of approximate practical methods. Of course, that's interesting. It's important to have approximate things in order to have a qualitative picture of what's going on in the material. But nowadays, the trend in physics, somehow it's based on computation. We do have access with very powerful computers, and somehow nowadays it's not enough to have a qualitative picture of what could be the physical property of the system. For example, it's not enough to say nowadays if some material could be a superconductor or not. Nowadays, it's you're expected to say also something to predict the expected TC, the transition superconducting temperature of this superconductor, and these kind of calculations are based on the main subject of this course, which is density functional theory. So the reason of why nowadays many kind of research that's done on the materials is relying on the computer power is this theory, is the density functional theory. In order to see in a graphical way the success of this theory, I'm just making a figure of the number of publications of just based on density functional theory as a function of the year. It was taken from the Web of Science. Okay, just keep in mind that that theory was proposed in the 60s, and also there were proposed several starting points, several initial exchange and correlation functionals. But was not until the 90s where the success and the enhance of the number of publications started, where that was when the first implementations of exchange and correlation functions were proposed, LDA and GGA, which make that theory, density functional theory, to be applicable to different systems. And of course, it has to be also related with the access to computing power. And since then, since the 90s, you could see that the number of publications that's related to density functional theory, it has been increasing exponentially until nowadays, and it's keeping increasing exponentially. So somehow we could say that the theory we have been describing in this course, it somehow is the theory that's used in order to analyze and predict the physical properties in the materials. Of course, it has many drawbacks yet, because it's difficult to apply them to highly correlated systems and so on and so forth, but the kind of predictions and the success on different predictions that have been made with this theory is astonishing. And what's going to be the future? Okay, that's difficult to say, but we could say which is the trend in the last years, and probably that trend is going to continue in the following ones. Okay, the recent years it has been proposed more and more accurate, more and more complex at the same time exchange and correlation functionals to make density and functional theory to be applicable to more and more complex systems. And of course, that started from the very beautiful and very simple proposal, which was the LDA. And related to that, we have the GGA, the meta-GGA, the exact exchange. Some of them we have already commented on them during the course. There are more complex ones, which are based, for example, on the random phase approximation response function and so on and so forth. And actually, these kind of different approximations for the exchange and correlation function, that's what Purdue called the Jacobs ladder. And actually, that name, he took that name from the Genesis book, where there is a passage in the book which said, "And he dreamed, and behold, a ladder set up on the earth, and the top of it reached to heaven, and behold, the angels of God ascending and descending on it." Okay, that applied to density functional theory would be like the earth would be like the Hartree approximation, which more or less is the classical approximation. And then we have the steps on the ladder. We have different approximations starting from the LDA and so on and so forth. And then there is a dream on that ladder that at some point we could be able to reach like close to the exact exchange and correlation functional, that would be like reaching to heaven. Because once we have that, any property of the system, of any system, could be described, could be predicted, just applying density functional theory. Okay, we don't know if we could be able to reach that dream or not, but our main aim here in this course has been to give you like a general perspective of what density functional theory is and which are the different approximations that nowadays can be are applied to analyze different properties of the solids in order to make you apply density functional theory to analyze them. Besides that, which is also very important, to know what are you doing when you are applying them.